Hello, welcome back. Today we're going to talk about critical numbers and extreme values. Critical numbers are places on the graph where something is happening. And we defined them earlier this year by saying a critical number is where the derivative is 0 or where the derivative itself just plain and simply just does not exist. And we have a lot of places where this can happen. Obviously, if the slope is 0, we have our horizontal tangents. And that could look something like this. But we can also have vertical tangents. And that could look something like there. And we also have corners and cusps. They could also work as well. These are points on the graph where something is happening to the derivative. So I can have a cusp, I can have a corner. But the most important thing to remember is the function must be continuous. So the only rules that we have, the only no-nos that we have, no-nos here, are going to be no holes and no asymptote, or vertical asymptotes in this case. Be careful, vertical asymptote, not a vertical tangent. And the other thing we're going to take a look in terms of critical numbers, and this is going to help us out later on, no endpoints. We're going to talk more about that later on in just a few moments here, okay? So no endpoints for a critical number. Those are the no-nos. So let's take a look. We want to find the following critical numbers for the following functions here. So we're just going to take the derivative. So if I take the derivative of 5x cubed plus 5x squared plus 9, we're going to get 15x squared plus 10x. To get the critical numbers, watch what I do here. Our rule, set the derivative equal to 0 and set the derivative to a d and e. If we set the derivative equal to 0, I'm going to do a little bit of math here. I can factor out a 5 and an x. And that's going to give me 3x plus 2 equal to 0. In terms of d and e, when we talk about d and e, really we're just talking about division by 0 or negatives under a radical. There's none of that here, so we're not going to worry about that for this situation. Solving, I now get two answers. I'm going to get 5x equals 0. And 3x plus 2 equals 0, and that's going to give us 0 and negative, not negative 3, negative 2/3. And those are our two critical numbers. So let's talk about trig. Be careful for this one. We do have a chain rule here. So when we take our derivative, we would get cosine 2x, and the derivative of the inside is 2. So once again, to get our critical numbers, we set the derivative equal to 0, and that's just taking this cosine 2x times 2, set that equal to 0, and where does the derivative just not exist? And in this case, again, cosine's pretty much available anywhere. So I'm not going to. So when I look at the first critical number, I'm not going to worry about the 2. It's just going to divide out. So I just think, well, where is cosine equal to 0? Well, cosine is equal to 0 at pi over 2. 3 pi over 2. Be careful, this is I got to go around twice. So that's going to make this 5 pi over 2 and 7 pi over 2. Be careful, this 2x right here says we're going around that unit circle 2 times. So this is 1 time right here, and there's the second time. And now I divide by 2. I get pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Know thy trigs. Now we typically have our domain only go from 0 to 2 pi. So all those would work. But what if we did 0 to pi instead? Well, in that case, the last two just won't work. We don't have to worry about those. All right, well, we would just cancel them out. All right, so for number 3, this is where we start talking about where the derivative does not exist. When we take the derivative, be very careful. When we drop this down, this is going to become 40 over 4, or 10x, subtract 1. 5/4 minus 1 is 1/4. Minus, drop the 1/2, that becomes 8 over 4, or 2x to the negative 3/4. Rewrite this. I'm going to rewrite this as 10x to the 1/4 minus 2 over x to the 3/4. And what I'm going to want to do is I'm going to want to write this as a single fraction. My common denominator is x to the 3/4. So to get my common denominator, I would need to have another x to the 3/4 down here, or under the 10x to the 1/4. So I have to multiply the top and bottom by x to the 3/4, and if we do that on the top, we would just get 10x minus, this already has my common denominator, so it just stays the same as 2. There's our single fraction. Let's take some practice right there. To get your critical numbers, where does the derivative equal 0? Well, for this, we just look at the top of the fraction. We've done this before when we did implicit differentiation, where if you look for the derivative is 0, that's where dx is 0, or dy is 0, that's just the top. So we would get 10x minus 2 equals 0, or x equals 1/5. Likewise, if I want to find out where my derivative does not exist, now I'm going to look at the bottom of my fraction. That's where my vertical is going to be. And this is going to give us x to the 3/4 equals 0, x equals 0. So we have our two critical numbers. Now, I will tell you, you want to write this as a single fraction, otherwise we tend to lose out on that one right there. All right, take a pause and let's take a look here. All right, so why do we like critical numbers? Well, a critical number helps us to determine where we have a maximum and a minimum value. Now, there are two types of maximums and minimums. We call them absolute and relative. So let's look at the graph below to help explain the difference between the two. So, when we talk about absolute maximums and minimums, for these, if I were to look at the graph, tell me what the highest and the lowest point is. And that's really what this is. What is the absolute highest and absolute lowest point on a graph? And I can see that. I can physically see that. Now, for these, we are going to use the values themselves. In other words, we're looking at the function. And if I were to take a look here, I can actually kind of pinpoint it. My highest point, it looks like it's going to be here. So there is my absolute maximum. And it's at the point 4, 5. And I can write that out here, 4, 5. My absolute minimum looks here. There's my absolute minimum. It's the lowest point on the graph. It doesn't matter if it's a corner or a cusp. It's a point on the graph. And this is going to give us 2, -6. Right there. Now, when we talk about relatives, sometimes we call relatives minimum, local. In other words, we're within a certain vicinity. Now, I know that this is my absolute maximum, but are there other maximums that are relative to a certain region? And most of you guys would probably say, oh look, at -1, there is another maximum. Yes, this is another maximum value. This is called a relative max. This is called a relative max because within its local area, it's the highest point. Like if I only look at a certain bit of it, it's the highest point in that region. Now, there is another relative max. And this one's always a little bit tricky. It's this one. It's the point 4, 5. This is also a relative maximum. I know what you're thinking, but we said it was the absolute max. Yes, and that is true. So, let's talk about the definitions between them. Remember when we said that the absolute maximum is the highest point on a graph? Well, how we define a relative max, a relative, this is where we are just changing direction. We want to find or look where the function changes direction. And that's all. For this one, we use the derivative of the graph. We're going to look at the derivative, the slope. And this is a relative max because notice I'm going up right before it and I'm going down right after it. We call that a relative maximum. Now, so what we just learned is that a relative max and an absolute max can be the same point, because one deals with the function and the other is going to deal with our slope changing. We'll talk more about that in a future video. So to find the relative maximums, well, we're going to have two of them, -1, 2, and 4, 5. 4, 5 just also happens to be the absolute max. So what about the relative minimums? Well, over here, you might guess that in the local area, this is a local minimum. It's a smaller area in a certain region. So we can say that this is a relative minimum. But don't forget, even locally, I'm changing direction over here as well. At my absolute min, I'm going down and then I'm going up. So this is also a relative minimum. So we have a relative minimum going to be at -3, -2, and the point 2, -6. Now, a couple of things, okay? Now, we haven't talked about this. We're going to see this in the next example, but relatives cannot be endpoint. Can't be endpoints. Now, let's talk about why. That kind of goes back up to here when we said no endpoints, because we're talking about the change in the slope. If I'm at an endpoint, can my slope ever change direction? No, it's going down here. We don't know if it's going up. So we say relatives cannot be at an endpoint, and that's very big for us. And then again, that is because there is no change in direction. And there we go. Now, another way that we call absolute, we call them extrema or extreme values. Very easy to do. All right, so let's look at this graph. We want to use this graph to find any absolute maximums and absolute minimum values if they occur. If not, write D and E. So if I'm looking for the absolute max and mins, remember, for these, we're looking at the values of the graph. Where is the absolute biggest point of the graph? And that looks to be at this point right here, at the point 6, 8. I'm going to write it as a point 6, 8. What about the absolute minimum? Well, take a look. This looks like it might be the absolute minimum, but if I go over here, notice it goes down a little bit further. This is an endpoint, but it does have a value. So, because it has a value, my absolute minimum is actually going to be at an endpoint this time. When we talk about candidates test tomorrow, we're going to talk more about this, where it is that absolute max and mins must occur. Endpoints are one of the options. And this is going to be 9, -6. When we're looking at the relatives, now remember, the relatives are different. Here we're looking at values. Now let's look at the relatives. Here we're looking for just a change in direction. Again, we're going to be more specific about this later on. So my relative max, well, that looks like it could be here. It looks to be at the point 1, 3, but don't forget, this is also considered a relative max because I am changing direction. So I am also going to get the point 6, 8. So let's try this, the relative minimum here. What about this? A relative minimum, it looks like it could be -2, -1. Looks like there might be a few here. Looks like at the point 2, -4, because I'm changing direction and I'm at a bottom. And let's see, are there any more? What about the endpoint? Will this be considered a relative minimum? No. Remember, for these, no endpoint, because the direction doesn't change for us, so we're not going to accept those. All right, go into the second video and we'll finish these up. I'll see you then. Bye.